Today, we are diving deep into one of the weirdest, most powerful features of our universe, quantum entanglement. But we're going to explore a really fascinating twist on it, asking a question you might not have thought of. What if this fundamental connection has a hidden vulnerability? So let's get right to it. We're going to probe the very fabric of reality by asking this simple but kind of profound question. Could the strangest link in the cosmos also be its weakest? This is the central mystery we are unpacking today. All right, first, a super quick refresher. You've heard of quantum entanglement, right? It's that spooky action at a distance that famously weirded out Einstein. You've got two or more particles that become linked. Their fates completely intertwined. You measure one, and you instantly know what's up with the other, even if it's on the other side of the galaxy. So how in the world do you test something as fundamental as entanglement? I mean, you can't just poke it with a stick, right? Well, some brilliant scientists at Chiang Mai University came up with a wild thought experiment. What if we could just ever so slightly tweak the basic rules that govern light itself? To even think about that, you gotta know about something called the Lagrangian. Now, I know that sounds super complicated, but just think of it as the universe's official rulebook for electromagnetism. It's like the source code that tells light how to behave, how photons travel, how everything works. So here's what the researchers did, at least on paper. They imagined introducing a tiny little deformation to this rulebook. It's like finding the source code for reality and adding a single, almost unnoticeable typo. This isn't just a random change, though. It's a really clever, controlled way to perform a cosmic stress test on the laws of physics. And the whole point of doing this? To see what happens to that spooky connection of ours. You know, if you nudge the fundamental laws of the universe, even just a tiny bit, does that delicate fabric of entanglement start to fray? Does it tear? Or does it actually hold strong? To answer that, we need to look at two different types of entanglement, because believe it or not all quantum links are created equal. So let's meet our two contenders for this cosmic stress test, the GHZ state and the W state. So on one side, you've got GHZ states. Think of this as an all-or-nothing kind of deal. All the particles are locked into one single giant connection. It's a group bond. Then you have the W states. Here, the entanglement is shared. It's distributed among all the individual particles. It's more like a peer-to-peer network. And here's the best way to picture this. A GHZ state. It's like a beautiful, incredibly intricate crystal sculpture. It's gorgeous, but if you chip one tiny little piece, the whole thing can just shatter. A W state, on the other hand, is much more like a chain link fence. You can go and cut one of the links, but the rest of the fence stays connected. It's just built to be more resilient. Okay, so the stage is set. We've got our cosmic stress test, that little typo in the laws of physics, and we've got our two subjects, the fragile crystal sculpture and the tough chain link fence. It is time for the verdict. Let's see which one breaks. This is the moment of truth. When the researchers applied that tiny deformation, that little typo in the laws of physics, which form of entanglement gave out first? Which one shattered? And which one held on? And wow, this graph tells the entire story. On the vertical axis, you have how much entanglement is left. On the horizontal, you have how big that typo in the physics is. Now look at that blue line. That's our GHZ state. It holds on for a second, and then it just drops off a cliff. But the red line, the W state, see how it degrades so much more gracefully? It's a nice, gentle slope. So the bottom line is this. The crystal sculpture shatters. GHZ entanglement is incredibly fragile. It breaks down really, really fast when the rules of physics get even slightly tweaked. The chain link fence, that W state, proves to be way more robust. It loses its connection, sure, but in a much more steady, predictable way. And if you want to see the math, it's pretty clear. The GHZ state's loss is quadratic, meaning it accelerates, and fast. The bigger the system's particles, the more fragile it gets. But the W state's loss is just linear. It's much more predictable, more resilient. It's all about how they're built. Okay, so one type of entanglement is fragile. You might be thinking, so what? Why does this matter? Well, this is where the story gets really, really exciting. Because this isn't just some academic curiosity. This might actually be a roadmap to discovering entirely new physics. I mean, listen to what the authors of the paper themselves said. This sensitivity, this fragility, could be used as a probe. We can essentially turn this weakness into a scientific superpower. Let's totally reframe this. The extreme fragility of the GHZ state, it's not a bug, it's a feature. Because it's so incredibly delicate, it acts like a cosmic canary in a coal mine. It becomes a hypersensitive detector for any tiny, tiny deviation from the physics we think we know. And here is the actual game plan. Step 1, you create these ultra-fragile GHZ states right in a laboratory. Step 2, you measure their entanglement with insane precision. Then, step 3, you just watch them. And if you ever see an unexpected drop in entanglement, a drop that standard physics absolutely cannot explain, that could be your signal. That tiny flicker could be the very first evidence of a typo in the universe's rulebook, a sign of new physics we have never even dreamed of. So we're left with this absolutely tantalizing possibility that the very thing we thought might be a weakness, this incredibly fragile quantum connection, could actually be our most powerful tool yet for peering beyond the known laws of science and discovering the universe's hidden source code.